Let's start with the basic of sound waves, and in fact, really all waves, but we're focused specifically on sound in this class. We're going to cover what frequency means, what wavelength means, wave velocity, speed of sound. All of these are part of where we are in this one. And what symbols are we using in this? What are our units in this? Well, F is what we're using for frequency. The units for that are hertz or 1 per second. A hertz is just 1 per second. Frequency often, um, how often something happens. Period, T. A period is going to have units of seconds, and the period is how long it takes for something to happen. And lambda, the Greek letter lambda, that's meters, and it's for wavelength, which is the distance from peak to peak. So if you're looking at ocean waves, the distance from peak to peak is lambda. Wave velocity, V sub W. Wave velocity is meters per second, and it's how fast a wave is traveling. And in most of the times, we're going to be talking in this in terms of the speed of sound, which is not a constant. The speed of sound depends on temperature and air. It also depends on other materials. So if your speed of sound through aluminum is much faster than the speed of sound through air, speed of sound through water is different than the speed of sound through air. Speed of sound depends on the material it's traveling through and other properties of that material. And wave amplitude. And so here I have y as a function of t, as a function of time. Later we'll look at it as a function of time and position, but it's in meters, and it's the displacement from rest of a wave as a function of time. And then A is our maximum wave amplitude, and that's also in meters. Now, when we think about sound waves, meters is a very large unit because sound waves don't really displace in meters. They are much, much smaller than that, and they're transverse waves, which we'll talk about at when we get into interference and how sound works a little bit more. They're transverse waves, and you'll play actually at some point with a slinky and transverse waves. Some equations. Frequency is 1 over the period is 1 over the frequency. The wave velocity is lambda times frequency, or wavelength times frequency, or the wave velocity can also be written as wavelength over period. Let's look at, and this picture is in the time domain, so at the bottom it's time in seconds. So this is not in the physical domain of distance, this is just in time. Waves are basically a sine function. So if you be at one point in space and look at a wave going by over in time, it would look like this. You'd be going, like say you're a duck on the water, you'd go up and down and up and down and up and down. And in time you do this, but in space you're just sitting in one spot going up and down. The basic equation for this sine wave, you got your amplitude, you've got 2 pi times your frequency times whatever the time is. If you look at the time scale on this slide, we go from 0 to 0.1 seconds, or a tenth of a second. So 1 period is peak to peak in time. So if you look at this, 1 period is from here to there. Well, how many periods do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got a total of 10 waves here. If we start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 complete waves. So a period is 0.1 seconds divided by 10. So 1 period in this is 0.01 seconds, which is 10 milliseconds. All right. What's the frequency? Well, we have 10 waves per 0.1 second. So 10 divided by 0.1 is 100. This is a 100 hertz wave. I'm actually going to give you the spreadsheet I used to generate this so you guys can play around with it some. Right? So this is a 100 hertz wave with an amplitude of 1. Right? And again, the amplitude is not peak to peak where you would get 2 here. The amplitude is from the neutral position to the peak. Right? So we have an amplitude of 1 here. So basic sine function, here's 100 hertz, here's 200 hertz, 300 hertz, 10,000 hertz, and you can see the time scales are so different for different frequencies, right? The time scale for this is a tenth of the time scale for that. And then you go up to 10,000 hertz and 25,000 hertz. And so when we talk about frequencies, we don't often really look at them in a time domain because the time scales for different things, for different sine waves, for different frequencies are just so different. It makes no sense to look at them on this in the time domain a lot of times, because if you got this going on with that, it's really hard to tease out what's really going on. Let's take a look at what it looks like. All right. The cool thing about waves is they simply add. So if I've got two waves, A1 sine 2 pi f1t plus A2 sine of 2 pi f2t, here I've got a 100 hertz wave and a 300 hertz wave, and I just add them, I get something that looks like that. And these are the same amplitude. Oh, nope, sorry, this one's half. 0.5 is the amplitude here is 1. You can see occasionally they line up because 1 to 3 ratio gives you the occasional synchronous. Well, occasionally they're completely in phase and they add up to 1.5, or they subtract all the way down to minus 1.5. And so you get a shape like this. All right. Imagine adding more and more in there. You can't really tease out from this picture, from the time domain, what's going on in terms of the frequencies involved. It's very hard to do, which is why later on in the semester we'll look at fast Fourier transforms and look in the frequency domain. Here's one you'll see a lot. So this is a 300 hertz wave. This with an amplitude of 1. This is a 60 hertz wave with an amplitude of 0.1. And you can see here that you can see from this envelope that basically you've got a 300 hertz wave riding on top of a 60 hertz wave. And so you'll see this kind of structure where you've got, if you were to actually just draw this, see if I can do that, and plot that wave, you would find out, oh, that's 60 hertz noise sitting in among my signal at 300 hertz. And I've got this clear 60 hertz, because if you measured that distance, you'd find out that that was one period, or 1 over 60. And so you can clearly see the 60 hertz noise with the stronger signal on top of it. When you get down to lower frequencies and you're looking at what's going on in a time domain, you'll see this quite frequently. May mean you have to turn off a piece of equipment, may mean you have to turn off the fluorescent lights, all kinds of things it may mean. If we look at waves in both space and time, which is where they really exist, the full equation for them is the wave y of t is a sine of 2 pi f times time minus 2 pi over lambda times x, if this wave is moving back and forth or in the x direction. All right. If you like symmetry a little bit, you can write it in terms of the period instead of the frequency, and it's just 2 pi over t times time minus 2 pi over lambda times x, and that gives you a little bit more symmetry if that appeals to you. If you're traveling in the minus x direction, that minus sign changes to a plus. So this wave up here, that's traveling in the plus x direction. That's traveling in the minus x direction. Why is that? Well, if we look at a wave traveling in the plus x direction, and you want to, let's say you want to sit on top of a peak on this wave and stay on top of that peak. Let's say you're a surfer and you want to stay right on top of the peak of the wave and stay in the same position. Well, to stay in the same position on the wave where the amplitude is always the same, and that should actually have a t comma x in it, where the amplitude is always the same, for any little change in time and change in position, this inside the brackets has to have the same value. All right, that has to have the same value. So if I go here and I say, okay, I've had a little change in time, and I've had a little change in position, and I want this, if I'm at the peak of the wave, I want this to be 0. And so I start solving. 2 pi f delta t is 2 pi over lambda delta x, right? Delta x over delta t, 2 pi f over 2 pi over lambda. Well, that ends up being f lambda or lambda f, all right? That ends up being lambda f. Well, delta x over delta t is just the velocity of the wave. It is a velocity. It's the velocity of that point at the top that you're sitting on top of as the surfer. So the wave velocity just ends up being f lambda, or, as I wrote earlier, lambda f. If you have the plus sign here, all right, what changes? Well, if you've got a plus sign there, let's go. I'm going to put a plus, right? So that's plus. Well, if that's plus, then over here you have a minus sign, right? Because this would be plus. That's plus. That's minus. The minus is still over here. The minus is there, right? The minus is there. And so you've got your wave velocity is minus lambda f, or negative. And that just tells us that the wave is headed in the minus x direction. Okay, hopefully this overview helps get into the problems. You're going to have some problems involving the spreadsheet I use to create these different graphs, and you're going to play with it some. And hopefully you're going to have a lot of fun. Talk to you later.